All right, so in terms of recap for the beginning of MLA I, right? You remember we started with the kind of the reliability piece, right? So if you remember, if you reach back to the beginning of day one, it was how do machines fail? And we said it was roughly, what was it? The break was about 15% was obsolescence. Yeah, and then we said that there was probably another 15%, which is roughly accidents. But the vast majority of it, let's say the big number, 70% was surface degradation, right? Of which there's sort of two major buckets. One is corrosion, right? And the other one is, yeah, like physical wear, basically. And we'll talk a little bit more about the different wear modes later today. And if you remember, if you want a tip for the exam, anytime we're going with numbers, it's always like the number that makes lubricants look the most important or makes the lubricants look the best, that's usually going to be the correct answer, right? So 70% roughly sort of like corrosion and wear. We then went on to talk about the different kinds of maintenance and how the role that lubricants plays, right? So we threw out some numbers, you know, it was what, 80% of hydraulic failures are attributable contamination. 80% of bearing failures have some kind of relation to kind of a lubrication related event. And then we started talking about the P to F curve. So there was this idea that we have a machine which has some amount of usefulness, right? Then we have some event, which the reason it's called the P to F curve is because this is the P, the problem, and then it falls off to F, the failure, right? Now, we've kind of changed the way that we talk about this. So the language of the P to F curve has changed a little bit. What people now say is rather than problem and failure, they might say something like, here is something called the incipient failure, right? And here is the catastrophic failure. So the idea is that the machine there is a fault or a failure that has occurred, and it's going to degrade until the point where it's completely kaput. Right? And if you remember, we had a whole bunch of different kinds of maintenance. So reactive maintenance was we're just going to fix this thing once it fails. So we're going to operate in this region, right? Not always the incorrect answer, but it is generally the one with the highest cost, right? So we're acting right at the end of the curve. Most of the time we're having to replace, you know, the asset or the part. Then we had, what was it? Preventative, right? So that was when we're just going to do our maintenance events at standardized intervals. So it's like changing the oil every 10,000 Ks on your car, changing a gear oil every 6 months. We're going to standardize that across the board. Now remember, the downside of doing that is that we have maintenance-induced failures. So as an example, we're going to talk about contamination control today. In some cases, if I open up the gearbox and put new oil in, number one, that introduces a failure point, right? What if someone contaminates it with the wrong gear oil, or they put a hydraulic oil instead of a gear oil? What if we open up and, let's say, for example, we forget to put the lid back on? I've seen that happen a handful of times. In mining, you just get a whole bunch of dust, iron ore dust blow in, right? It's abrasive, right? So that's maintenance-induced failures. Then we move on to the next one, which is predictive, right? So in predictive, we're actually doing sort of like maintenance events, if you like. Let's say, for example, like we're doing inspections, and we're trying to pick up what you might call the incipient failure before it becomes a catastrophic failure. So this is all our condition monitoring tools. It's your oil analysis, it's your thermography, it's your ultrasound. It's these days you've got, obviously vibration analysis. There's the motion amplification cameras that we talked about as well. So there's a whole range of different technologies that are going to help you there. And what's the final one? Proactive. Proactive is we are acting basically in this portion of the curve, which is to prevent the failures before they ever happen, right? So if statistically we know 80% of hydraulic failures are caused by contamination, hey, if we do everything that we can to prevent contamination of the asset and of our oil, we are acting to kind of nip it in the bud, for want of a better word, right? So we are acting in this front portion of the curve. That's the most, I say most expensive. It's probably got the highest upfront cost because you're paying for things like filter carts, you're paying for things like storage areas, right? But the idea is that the overall cost to your business is going to be significantly lower. All right. Then we moved on to a discussion about actual lubricants. If you remember, so lubricants, yeah, we basically divide them into, what was there? There was mineral types, mineral, right, and synthetic, right? And there were base oil groups, right, which talked about mineral and synthetic. So you had 1, 2, 3, 4, and 5, right? So 1, 2, and 3 are the ones where crude oil comes out of the ground. We talked about that as being like a box of Lego, right? All different molecules, shapes and sizes, and then we refine it, and the refining process kind of gives us the Lego blocks that we want. And the idea was that if we go from 1 to 3 to 4, broadly speaking, right, I'll put it in inverted commas, the quality increases. What that generally means is you go from 1 to 2 to 3 to 4 is that the stability increases, yeah, the viscosity index also increases, and the number of contaminants, the amount of contamination goes down, right? We talked about that mostly in terms of the sulfur content. Group 4 is its own special group. That is the synthetic PAOs. PAOs are the most common synthetic oil on the market. You guys in mining will most likely see it in things like gear oils, right, is predominantly where you'll see it. Also in some compressor oils, turbine oils and things like that. And group 5, what was that meaning?
Everything else.
Absolutely everything else. So sometimes it's really good, sometimes it's absolutely terrible, right? So everything else falls into here. So it's your vegetable oils, it's your esters, it's your PAGs, it is your silicons, right? All of that stuff fits into the group 5s. All right, so that was kind of like the base stock groups, if you remember, okay? So, yeah, and then we talked about the fact that now, so that's the base oils, and then we want to put additives in. Remember, so that additives are like the secret herbs and spices. We said proportionally, engine oils might be 80% base oil, 20% additive, or 90% base oil, 10% additive. Once you get into hydraulics, slightly lower, maybe sort of 4-ish, 5-ish percent. Compressor oils are usually 99% base oil, 1% additive. If you remember, the way that we construct an oil, okay, first of all, we have to start with our base oil, right? The next thing that we do is we have to protect the base oil. So we add, does anyone remember what that is? That's rust and oxidation inhibitors, right? So the rust and oxidation inhibitors are there to protect the base oil primarily, right? So think of that. I have a base oil, okay, the first thing I need to do is protect it. The next thing might be, if I have a little bit more load in the application, now I've got to protect the surfaces against wear, right? So therefore, I'm going to use anti-wear, right? So pretty simple, everything's very descriptive. And although anti-wear and EP are kind of different things, basically what we say is if it's even more heavily loaded and it can overcome the capacities of the anti-wear, I'm going to add extreme pressure. So basically, if the pressure is too extreme for anti-wear, I need extreme pressure additives, right? And then finally, if I have a very contaminated environment, right? So I'm producing a lot of stuff, contaminants. Let's say, for example, in an engine, finally, I'm going to add detergents and dispersants, right? And basically, as you go from the top all the way down to the bottom, we are increasing the amount of additives. So you pretty much are never going to go backwards. You're never going to have an oil that just has base oil and detergent. You're pretty much going to, these are sort of additive. You keep going, right? Now, the question is, why don't we just add all of this stuff every time we formulate an oil? Number one, the additives are the most expensive component in the oil, right? So you're just adding extra cost every time you do that. Number two, sometimes there's too much of a good thing. We talked about what's the predominant anti-wear that's in use? Something called ZDDP, right? Zinc dialkyl dithiphosphate, right? So if you add too much of that stuff, you can run into corrosion problems. Yep. So that would be one example where you don't want to use it. If you add lots of detergents, you remember detergents bridge the gap between oil and water-like particles, right? They're attracted to things like contaminants and water. So you can create emulsions where you might not want them. So in a lot of, let's say, hydraulic applications, gear applications, you want the oil and water to separate. Detergents are going to prevent all of the oil from separating. Okay, so that's the basics. Then we moved on to greases. Yep, so remember, grease is, you have oil, you have additives, and then you have the thickener, right? The thickener is really the only component. A lot of the time it's called a soap, right? The reason we call it a soap is because the vast majority of thickeners are soaps themselves, right? They're usually based on some kind of metal, right? So there's like lithium soaps, there are calcium soaps, there are aluminium soaps, there are barium soaps, there are sodium soaps, and so on and so on. The main one is lithium. Makes up about 70% of the market, right? Yeah, lithium and lithium complex added together makes up about 70% of the market. And that's because lithium doesn't really have a weakness. It's not outstanding at anything, it's just not bad at anything. Because if you remember, most of the calciums, right, this is standard calciums, don't do well in the presence of high temperatures. So above about 70 degrees Celsius, the water comes out of the thickener. The aluminiums sometimes suffer at high temperature shear, right? They tend to have shear instability issues. Barium had some toxicity issues. Sodium doesn't do well in the presence of water. So each of these kind of has an Achilles heel, whereas lithium does pretty well across the board. If you remember, if we want to mix greases, right, we want to pump in one after the other because we're doing a change. We had those compatibility charts. Do we trust them? No, generally not, because number one, they conflict with each other because everyone's using a different test method, even though there is a standard ASTM test for doing it, but also because that information didn't tell us anything about the base oil compatibility or the additive compatibility as well, if you remember, right? So that's the greases. There are also, if you remember, so you had separate to the non-soap, you had the polyureas. There were also the calcium sulfonate complexes, and then there was the clay-based greases. Clay will also be called non-melt, bentonite clay, or organoclay. They are all referring basically to the same thing, right? Often used in high temperatures. Calcium sulfonate complexes are often used in high load conditions because the thickener is a solid lubricant. And then you've got the polyureas. These don't contain any metals and therefore are often quite stable over long periods of time. All right, so that's the greases. If you remember, in terms of classification systems, right, now we can talk about the viscosity grades, right? So the viscosity, most important part of a lubricant, right? And we had different naming conventions, right? So there was the isoviscosity grades, yep, and we also had the SAE viscosity grades, if you remember, yep. So SAE is for the automotive stuff. Yeah, your engine oils and your automotive gear oils. The ISO grades are the ones that you're going to see in most of your industrial stuff. Now, if you remember, there was two different types of viscosity. You had the absolute viscosity and the kinematic viscosity, right? So the absolute viscosity is in centipoise, kinematic viscosity, centistokes, right? The absolute one is the one where we put kind of like a spindle inside of a cup, we spin it, and that's how we get centipoise. Whereas kinematic, we like that one because it's just a big U-tube and you just measure how much time it takes to drop, right? So it's a faster, more repeatable one. Kinematic viscosity at 40 degrees Celsius is what gives us the isoviscosity grade, right? So when we measure at 40 degrees Celsius, we get the isoviscosity grade. The isoviscosity grades go 10, 15, 22, 32, 46, 68, right? And then you just add a 0, 0, 0, 0, 0, 0, right? Then you go again, add another 0, 0, 0, 0, 0, 0. Yeah, and if you remember, each of these was plus or minus roughly 10%, right? So this one, if it was anywhere between 900 and 1100, it's considered an ISO 1000. Okay, for the engine oils, slightly different, right? Those ones were, if I have an SAE 40, that's called a mono-grade engine oil, single grade, right? If I have an SAE 15W40, that is a multi-grade engine oil, right? Because there's multiple grades. And if you need to visualize it, you're basically saying at cold temperatures, it's acting like a 15W, and at high temperatures, it's acting like a 40. Right, is the easiest way to remember that. If you remember, basically these numbers on the SAE grades went up to 60. Anything beyond that, that's a gear oil, right? So if you remember, if I saw an SAE 75W90, that must be a gear oil, right? Because the numbers are above 65. So as an example in the exam, they could give you these 3, there's usually 5 options, but let's say they gave you these 3 and said, which one of these is a gear oil? This one, right? It has to be. All right, on the ISO viscosity grades, basically the higher the viscosity, the more load it can take, correct? So we usually would say, if I had a hydraulic oil, that's probably between, let's say, 32 and 100 centistokes, roughly. It's where most of them are. If I had a turbine oil, that would be usually, let's say, a 32 or a 46. If I had a gear oil, right? Some of you guys have standardized everything to 320. We usually say the gear oils run anywhere between 150 and 460 centistokes. Right? Obviously way higher. So I gave the example of the open gear oils, which are like ISO 22000, ISO 46000 type stuff, right? So basically the higher the load gets, the more viscosity we need. Now, if you remember, right, in terms of the actual way that lubricants work, let's start off with a plain bearing. Yeah, it's just a circle inside another circle, and we'll put some liquid lubricant in here, right? Now, initially, when we have no speed, that thing is just sitting on the low side, right? And as it starts rotating, what's happening is it's metal on metal, right? So initially, you remember, high friction at the very beginning. Then as it starts to pick up speed, it starts to generate its own lift, and we get that separation. So the viscosity, the amount of friction comes down. And then eventually, if we keep getting faster and faster and faster, it's having to push more lubricant out of the way, and so it starts to increase. And that was what we call the Stribeck curve. So we had, initially, this was called boundary lubrication, right? And then we moved into mixed lubrication, and then we moved into hydrodynamic lubrication. Yeah? So if you remember, there's 2 different types. There's hydrodynamic and elastohydrodynamic. So in hydrodynamic, we often call this thick film lubrication. And if you remember, think of it as double-digit microns, the film thickness. If I had, instead of rolling element bearing, so let's do this, this would be called thin film lubrication, single-digit microns, right? And it's because the surfaces are what we call non-conforming, remember? So that surface and that surface are roughly parallel. This surface and this surface are not. So that's like rolling element bearings, gears, cams would be elastohydrodynamic. hydrodynamic lubrication. Right? And I think that is a speed run of everything that we did yesterday. So we didn't need to sit here for a whole day. I could have just gone through it in a half hour.